So now we are starting with balancing. Okay, what is balancing actually? Process of either fixing, removing or reducing the magnitude of unbalanced force or couple is known as balancing. Either add, what we are going to do to balance the system, we are going to add the load, add the counter mass or remove the unbalanced mass. Okay, so one terminology we must we must know that what is statically balanced system. Statically balanced system in the sense there is no unbalanced force, and when we draw the force polygon is a always closed polygon. Okay, always be a closed. So in balancing of the rotating mass in static balancing, suppose if you assume the mass also, when in the static balance system, the center of mass will be equal to center of rotation. Center of mass will be on the center of rotation. What is center of mass? Center of mass is generally when the point of when the mass of the body is assumed to be concentrated on one point, that is known as center of mass. The center of mass will be on center of rotation. Okay, suppose if a body is there whose center of mass is at eccentricity from center of rotation, now how can we balance this thing? Now what we are doing, we are taking one point, from one point at an angle at the distance of eccentricity, we are assuming the mass of the unbalanced mass. Okay, now if we rotate this mass, then mass of the rotor, if we rotate this mass, then the centrifugal force will be created, right, whose magnitude will be m r omega square. So to balance this mass, what we are doing, we are again placing the unbalanced we are placing the adding the counter mass, okay, of mass b, suppose say at a distance of b. I am not telling the distance as e, because it may be the balance distance may vary. Okay, that is the thing. Now these two for the forces must be same, bb omega square and mr omega square. Okay, these two values omega square cancel. Then if you draw the polygon, then the the size of the line will must be same. Okay, so you can see in the, you can refer the velocity force polygon. Okay, so static balancing of the system by more than one balancing mass. Okay, in one plane. Okay, so generally when we look at the previous concept, there was one point was missing, that if one unbalanced mass is present, then total system will be unbalanced. Okay, so if one balanced mass is present, then total system will be balanced. Okay, so if balanced mass is present, total system will be unbalanced, and if both are absent also, then also the total system is balanced. All right, so this is the thing, both must be present and both must be absent for the system to be to make the system to be balanced. This is the thing. So now what we are doing, we are placing more than one masses at different locations in one plane. Okay, such that the resultant of these two balanced masses must be same as the unbalanced mass. Okay, so generally there are two methods. Method number one is polygon method. In the polygon we are drawing. Okay, suppose unbalanced mass is making an angle theta, let mass be m. So m1 r1 m1 mr omega square, m1 r omega square, mr omega square, sorry. So mn is a mass which is used for balancing of the system. mn2 is a another mass which is used for the balancing of the system, and these two masses are making theta 1 and theta 2 and theta 3. All right, theta 1 and theta 2 with horizontal. So in the fourth polygon, we start from unbalanced mass. We draw one polygon at theta whose magnitude will be equal to mr omega square. All right, so again we start from theta 2 and we draw m1 r1 omega square, and we start with theta 3 and we'll draw m2 r2 omega square. Okay, these are the fourth polygon, and this forms a closed polygon. If it's closing, then we can say that this system is balanced. Next analytical method we can use by using the cos tricks. Okay, cosine tricks.
cosine sticks. Generally break the total forces in cosine and sine. All the cos terms like ME sin ME cos theta plus M1 R1 sin theta cos theta plus M2 R2 cos theta will be equal to 0. Okay, so this is the thing. And if you want to write in the sine form, then you can write it ME cos sin theta plus M1 R1 cos sin theta 1 plus M2 R2 sin theta 2 equal to 0. Okay, you can balance in this way by using this analytical approach. So this was the concept.
So when we talk about the static balancing of the system by adding mass in the parallel plane, so generally there will be a rotor which is rotating in the shaft. Okay, so when we look at the diagram number 1, so the centrifugal force is in the y direction, but we are representing the centrifugal force in y direction, but actually the centrifugal force will not be in the y direction. When we look at it in the when we look at from the side view, so that unbalanced mass will be in the from some distance of e. All right, from some distance of e. So to balance that system, it is lying in first quadrant. Therefore we are placing another mass in the third quadrant, right? With some angle theta 1, with some angle mass, with some mass b. So bb omega square will be must be equal to me omega square cancel it, bb equal to me. So now how we are placing this mass? So when we look at the first case, we were placing it in a parallel plane. We were placing it in a same plane, right? But here now we are placing the parallel planes. We are on the shaft. We are choosing one such a plane such that that plane will be parallel to the rotor, the plane of the rotor. Okay, at some distance a. On that plane we are placing on some eccentricity opposite to the first force. So we are representing in the vertical plane. When you look at the reactions which are known as dynamic reactions, the reactions are also not in the vertical plane. They are opposite to that centrifugal force. And now these planes, if they are at some eccentricity at some distance, if two forces are equal and parallel, then they will create one moment. Okay, then they will create one moment. So that moment is if we balance the moment, like summation of moment take equal to 0. When we take, then we can write it as r into l equal to me omega square into a. Why? Because me omega square into a by 2, me omega square bb omega square into a by 2. Since me equal to bb, then we can write 2 into me omega square into a by 2. A by 2 2 cancel, me omega square into a. So this is the moment. Alright, so this is how we are going to solve this kind of problem.
So today we'll discuss the remaining topics of the balancing. Alright. So we completed yesterday. We completed up to I think it was balancing the mass which is parallel to the shaft, right? Parallel to the plane of the rotor. Now we are discussing the dynamic balancing. Okay, so in the dynamic balancing, body is said to be dynamic balanced the uh, if the forces are balanced and also couples are balanced. All right, forces are balanced, also couples are balanced, then only we can say that dynamic balancing is done. Okay, previously we talked about the balancing, right? Previously we talked about the balancing balancing of the parallel shaft. In that we talked about the dynamic reactions. What are dynamic reactions? Dynamic reactions are those reactions whose sum is 0 and they are equal and opposite reactions. Okay, so the system when the reactions are equal and opposite, then we can say that it is static it is a static balanced system. Okay, it is not dynamic balance system. So here we need to balance the couples. Here we need to balance the couples and also the reactions. Okay, and as couple we are going to balance the couples and reactions, it will form a closed polygon, right? So generally now what you will do, not now, if you discuss about the question number 9, there will not be any reactions here. All right, because it is a dynamic balance system. Okay, it is there is no reaction here. There are no reactions here. Okay, so how to calculate the we must do the balancing of the forces and also couples. Okay, so now mass of A he has provided, and mass of D he has provided, and mass of B he has provided. Okay, mass of A we need to find out, and mass of B need to find out, mass of D is provided. Okay, and radius R is provided, eccentricity. So we will write form one table. Okay, mass of the A will be ma, then R radius will be 0.5, then theta A, which is making an angle theta, and mr cos theta. We are splitting it, mr sin theta, again L. Okay, length, then mrl cos theta, mrl sin theta. Then next D 2, it is acting at horizontal plane. Okay, therefore 0 degrees. Mr cos theta is 2, mr sin theta is 0, L is 30. Okay, length from left is 30, and 60, mrl cos theta 60, mrl sin theta 60. Okay, again mb 0.5 theta a, 0.5 ma cos theta, mr sin theta, L mrl cos theta, mrl sin theta. Generally what we are doing, we are selecting one reference plane. Okay, either A, D or B. Okay, uh, like we we generally take the reactions about one point, right? So to make that reaction at that point will be 0, we took the reaction at that point. Okay, so he similarly here we must take either B, A or B. We must select either A or B. So here A is selected, so length of A is 0. Okay, what is L actually? L of D is the length from the reference plane is known as L, and for B length from the reference plane it is 50. Okay, so like this we are done. Okay, now summation of forces. For the summation of forces we are generally equating the sign terms. Okay, ma sin theta A plus md sin theta B and mb sin theta B. Okay, like that. Okay, so if you sum up all those things, mrl sin theta we will get 25 mb sin theta. Wait. Alright, he did a mistake here. He took 60. Okay, actually mrl sin theta is 0. So if is summation of mrl sin theta we do, then 25 mb sin theta b. Okay, now generally from the two equations we are going to solve, we are going to form two equations, mrl cos theta, mrl sin theta. From these equations we are going to find one. From one equation we will get angle. If you substitute the angle at another equation, we will get total mass of the system. Okay, now 25 mb sin theta, if you look at 25 mb sin theta, mb must be 0, either sin theta must be 0. Mb can't be 0, right? Because we are balancing with the help of the balancing the unbalanced force system with the help of the masses. Mb can't be 0. Sin theta b can be 0. Theta b will be equal to, theta b is 0 when theta is equal to, sin theta is 0 when theta equal to 0 or 180. Alright, so next mrl cos theta. So if we talk about mrl cos theta, 25 mb cos theta b plus 60 equal to 0. So mb cos theta b equal to minus 2.4. So either mb must be 2.4, mb will be 2.4, and cos theta b. So theta b will be equal to 180, because theta b will be equal to 180, because cos theta b, cos is negative in the second coordinate, right? Cos 0 can't be minus 2.4. Cos 0 theta b can't be 0, because it is here it is cos. Okay, cos minus 180 gives, cos 180 gives you minus 2.4. Okay, so that's how we calculated mb. Now what you are doing, mr sin theta. Once we got mr, then if you look at mr summation of mr sin theta, there are two unknowns. Okay, ma, mb, sin theta a, theta b. Now we know mb, we know theta b. We know mb, we know theta b. Can we find ma and sin theta a from these two equations? Yes, we can find. So mr sin theta, so 0.5 ma sin theta a plus 0.5 mb sin theta b. Mb sin theta b substitute, we will get two unknowns, ma and sin theta a. Okay, now from the next equation, 0.5 ma cos theta a plus 2 plus 0.5 mb cos theta b.
So if we solve the first equation, then ma can't be 0, sin theta I will be 0. So theta I will be 0 and 180, 0 or 180. So if you solve the second equation for cos mr cos theta, yeah, we will get ma cos theta equal to minus 1.6. So theta I must be 180 degree and ma yields 16, 1.6 kg. Now system can be balanced by first method. Adding the masses, ma equal to 1.6 kg at 180, mb equal to 2.4 at 180. It's method to remove the mass. Okay. ma ma equal to 1.6 at 0, theta I equal to 0, mb at 2.4 kg at theta b equal to 0. That's the radar remove the masses. This how we solved for the dynamic. We did the dynamic balancing, right? Now balancing of reciprocating mass. So if you take the single cylinder engine, if you take the radius of the crank as r and omega, moving with omega, rotating with omega, and if you take the angle which is made by the crank with the line of stroke is theta, L is the length of the connecting rod. So generally there will be unbalanced force on the slider. Actually there will be unbalanced force on the slider. Okay. Unbalanced force will be the inertia of the slider. Okay. Now if you want to find the unbalanced force, F unbalanced will be equal to mass times A, right? Mass times acceleration of the slider. The mass of the slider into acceleration of the slider can be given by r omega square into cos theta plus cos 2 theta by n. Alright. So if you resolve these two forces, then we will get primary initial force and secondary inertial force. Once we plot the diagram at theta equal to 0 degree, then primary force will be maximum, and theta equal to 180 degree, it will cover 360 degree, right? 2 times 2 pi. At 2 pi, theta will F primary will be maximum. Okay. At 2 points, this F primary is maximum throughout the cycle. If we talk about the F secondary, then if you substitute theta equal to 0, then they will get maximum force, and secondary force throughout the cycle it is maximum at four places. Okay. Actually when you look at the from 3 pi by 4 to pi by 4, that is 1, and pi by 4 to again pi by 2, 5 pi by 4, that is different. Okay. Don't assume as 1. Now secondary inertial forces is maximum at 4 places. Okay. So frequency of the secondary inertial force is very large. Okay. So if it is dividing by n, so the magnitude of primary force is greater than the magnitude of secondary force. Therefore we are neglecting the secondary force. Okay. So to balance this primary force, what we are doing, we can't place weights, right? If the slider is moving with certain unbalanced force, weight okay. So direction of the unbalanced force is right side. Okay, at 180 degree. So now we can't place the mass directly opposite to the slider, right? What we are doing, we are assuming that if we place the mass on the crankpin, then that system will be balanced. Okay. So if we place the mass, what we are doing, we are placing the mass of the mr omega square, same mr omega square magnitude, and direction is theta. Okay. And if we split this into two components, mr omega square mr omega square sin theta, mr omega square cos theta is balanced. Okay. Now if you see mr omega square sin theta, and if theta equal to the like 90, theta equal to 90 degree, then sin theta will be equal to n mr omega square. If you see mr omega square, the primary force, that is the primary force, right? That primary force is not balanced, but we balanced the inertia of the system. So this is known as complete balancing. We are changing the direction. By changing direction, we are completely balancing it, but the magnitude of the unbalanced force remains same. Okay. Magnitude of the unbalanced force remains same. Okay. So direction is, by changing direction, we balance the force, but we didn't balance this maximum primary unbalanced force. Therefore, complete balancing not done in case of reciprocating mass. We must do the partially balance. Partial? By partial balancing, what we are doing, we are changing the mass and changing the eccentricity. Right? We are placing the mass. So now BB cos BB omega square cos theta, it balances MR omega. These two forces, resultant of these two forces balances the F unbalanced force. BB omega square cos theta itself will not balance. BB omega square sin theta will also the resultant of these two forces will be balanced. Okay, so generally if we talk about if we equate these two forces, right, BB omega square BB will be equal to C times MR. C is the fraction. Okay, whenever if we are getting this fraction, it means that this is partially balanced problem. Okay, so unbalanced forces along the line of stroke, if we equate, then we'll get Fx will be equal to MR omega square cos theta minus BB omega square cos theta. From here we will get Fx equal to 1 minus x MR omega square cos theta. This is unbalanced force along x. So unbalanced force along perpendicular to the line of stroke will be theta Fi into PV omega square sin theta. Okay, from the simple equation, you just remember this figure, you will get those equations. Okay, and resultant can be calculated. R will be resultant will minimum is equal to 1 by 2. Okay, next dynamic equilibrium condition. If you look at the connecting rod will be general plane motion. Therefore, it is difficult to consider the inertia of the connecting rod. For doing the dynamic force analysis, during the dynamic force analysis, the force acting the connecting rod must be replaced with the massless rod. Okay, actually the inertia of the connecting rod is difficult to consider the inertia because it is in general plane motion, will be not rotation as well as translation. Okay, that's why we are replacing this into massless rod. There will be certain conditions, I will talk about those conditions. So if we talk about the big end, so if you replace it with the mass of the rod, then center of gravity will be taken, center of mass, the whole mass is assumed to be concentrated. From those, the distance are taken as LB and LS. Okay, LB, why the nomenclature B as used, prefix B as used in the sense, it is the big end. So MS is a small end. Okay, mass of the big end, so it is replaced with some mass. Okay, we are putting some mass and mass of the small end. And note that mass of the big end, you may think that it is a big end, mass must be greater. Okay, it may not be greater. Mass of the small end, it is small, it may not be small end is connected with slider and big end is connected with crank. Okay, so now, and the small end can be partially balanced and big end can be totally balanced. Rotating forces can be totally balanced, reciprocating forces can be partially balanced. Okay, so now what are the conditions if you want to make the equivalent system? The total mass of the actual system must be equal to the total mass of the equivalent system. Okay, the center of mass from one end must be same, center of mass from only one end must be same. Okay, if center of mass is from 40, then here also the center of mass of the big end must be 40, distance between the center of mass must be 40. We can change the 40, the last problem we discussed. And next, the mass moment of inertia of the actual system and the mass moment of inertia of the equivalent system must be same. If the mass moment of inertia is not same, then we cannot say that it is dynamically equivalent system. Okay, to equate the mass moment of inertia, what we are doing, from one end we are considering the thing, and we are considering the radius of gyration of the other end. K will be equal to under root of LB into LS now. So LB we are considering length of big end. So length of the big end will be same, right, from the center of mass. What is the length of the small end? We are changing the length of the small end to make it dynamic equilibrium condition. Okay, so this is the thing. Next, right. So there are 3 points. Now mass of the connecting rod, I said that mass of the connecting rod previously must be equal to mass of this equivalent connecting rod, right? MB plus MS will be equal to total mass of the connecting rod. Okay, so now
the center of mass must be same. Okay, mb times lb will be equal to ms times ls. Okay, from here you can calculate the mass and mass if the gas provided. If you want to convert it into yeah. So I actual will be equal to I equivalent. I actual, what is I actual? Mk square is I actual equal to ms ls square plus mb lb square. Okay, so once we solve this, we'll get k equal to under root of lb ls. So now what is bb, sir? bb is the db. We are balancing the whole connecting rod. To balance the whole connecting rod, bb will be equal to mass times mr of rotating elements and mr of reciprocating elements. In rotating elements, mass of the crank plus mass of the big end is considered, and the reciprocating elements, mass of the slider and mass of the small end is considered. Okay, into r. Okay, so this is the thing. Now effect of the partial balancing in locomotives. Okay, there is 2 pages, we'll complete it as soon as possible. So effect of partial balancing in locomotives. In locomotives, 2 cylinders are used in order to obtain the uniform turning moment diagram. Okay, 2 cylinders are used. Those 2 cylinders are those 2 cylinders are perpendicular to each other. The crank of the cylinder 1 and cylinder 2 are perpendicular to each other. Okay, the balancing mass is attached on the wheels, and if n equal to L by R is very large, then the secondary inertial force can be neglected. Okay, this is some things. So variation of the attractive force and variation swaying couple. So if you take the first of all, if you talk about the variation effect of variation of attractive force, if we look at the diagram, fx1 will be equal to 1 minus c mr omega square cos theta. We know this. Okay, along the line of stroke force, along unbalanced force along the line of stroke, 1 minus c mr omega square cos 90 plus theta. Okay, this is along the line of stroke, right? A by 2, A by 2. Now, sir, what are you doing? Tractive force. Net unbalanced force along the line of stroke is known as tractive force. Fx net will be equal to fx1 plus fx2. 1 minus t mr omega square cos theta will be equal to 1 minus t mr omega square cos 90 plus theta. Fx net, we are calculating forces on x direction. So the whole balancing is it is one of the easiest topic, I can say. But to remember the formulas, they are directly derived formulas. They are derived from only one particular figure. Okay, so even if you forget, you just remember that particular figure. With the help of the remembrance of that particular figure, you can recapitulate that formulas. Okay, formulas are very easy. So if summation of force, if you take the summation of forces about x-axis, fx net will be equal to 1 minus c mr omega square cos theta minus sin theta. If you look at this, it is a function of theta. Okay, so fx net to be maximum, we must differentiate with respect to theta and equate to 0. If we equate to 0, we will get theta will be equal to 135 or 315 degrees. Okay, theta will be maximum or minimum at theta equal to 135 degree or 315 degree. This fx will be maximum or minimum. Okay, fx net at theta equal to 135 degree, if we substitute this, we'll get minus root 2 1 minus c mr omega. So theta equal to 315 will plus root 2 1 minus 3 c omega mr omega square. Variation of the attractive force can be given by plus or minus under root 2 1 minus c mr omega square. Attractive force is along the jerk along the so if we talk about the swaying couple, the unbalanced force along the line of stroke results in the couple. Okay, swaying couple in the sense there will be unbalanced couple. Okay, so if you take the couple fx1 moment about net fx1 a by 2 fx minus fx2 a by 2. Okay, if we solve this, we will get 1 minus c mr omega square cos theta plus sin theta a by 2. So function of theta, again we are differentiating, we will get 45 degree and 225 degree. At 45 degree and 225 degree, this moment is maximum or minimum. Okay, this couple is maximum or minimum. So we will get a by root 2 1 minus c mr omega square, we will get minus a by 2 a by root 2 1 minus c mr omega. Variation of the swaying couple is given plus or minus a by root 2 1 minus c mr omega square. So this is the swaying couple. Next, hammer blow. Generally when we talk about the wheels, okay, first of all what we did, n by L by R ratio, n if n is greater than 1, far greater than 1, we can say that secondary forces are imbalance, okay. And the wheels we are attaching the mass. Why we are attaching mass? This hammer below explains you, okay. The crank of the cylinder 1, cylinder 2 are perpendicular. So if the crank is perpendicular, there will be tractive force and there will be two forces, tractive force and swaying couple. Okay, we are swaying couple, we must balance the tractive force, we must balance the swaying couple. Due to the tractive force, there will be jugs will be produced, okay. Hammer blow in the sense, if there is a weight of the wheel, if it is rotating by omega, if there is an unbalanced force, there will be normal reactions, right? There will be unbalanced force. We are balancing this unbalanced force with the help of the some mass, okay. We balance it, okay. So there will be a normal reaction. So if we look at this unbalanced force, it is depends upon the omega. So as a n, if you equate for n, we will get W plus or minus BB omega square sin theta n. So normal reaction between the wheel and the rail is n. So as omega is increasing, then n is value is also increasing. N is increasing drastically. At one point the n value will be 0. At 1 omega n value will be 0. If n is increasing, if omega is increasing, omega squared, right? So n value will be increasing, and at one point it will be 0. Okay. So if it is 0, sir, then what happens? The wheels will left the road. Okay, if n is greater than, wheels will left. So omega value must be known. Omega maintained will be equal to root of W by BB. Okay, hammer ball results in jerks in the perpendicular direction. Therefore, maximum puts the limits of the maximum speed limit of the locomotives. Okay, so we must balance the wheel in such a way that the W must be maximized. Okay, W must be maximized. Okay. Alright, so this is the thing. Omega must be maximized. So W by BB under root of W by B. This is the limit of the omega. If omega is increasing, then n will increase. So square root of omega is increasing, then n will increase. At one point, decrease. At one point, the wheels will lose the contact. That will be dangerous for the driver. Okay. So last question, if you want to discuss the last question is, these questions are very, very simple. Okay, just to go through the concepts and revise it, analyze it. It will be very, very easy. So my job is to tell the concept, then your job is to solve the questions and analyze the questions. That is your job. And the test series person who is writing test series job is to recapitulate all these data analysis and uses all this experience in the test series to get good marks. And the next person job is to analyze the test series and send to here, and that person will check the notes, the particular mistake on the notes, each and every question. So again he sent to a test series person, and again he, with the help of the experience, he will write the test series until he gets the good marks. Okay, so this is the thing. So observation I actually will be equal to mk square. So here he tells you find the inertia. So you can't find the inertia directly. Okay, mk square by using mk square. Mass of the connecting rod, k is why? Because it is not dynamically balanced system, not dynamically equivalent system. To make it dynamically equivalent system, we are considering the length from the one side. Okay, 40. We are considering 40, and we are finding the length of the small end. We find the length of the small end, it will come to be 22.5. So we will get MB as 36 and MS as 64. So this is the thing. Next we will start the vibrations. Okay, this is all about balancing.